not for the ball.
Oh, sorry. The initial omega is 0 for the rod.
Yes. If it were for the ball, then it'd be a very simple problem. The final angular velocity speed is 0.
That's what. Well, can we, omega equals VR? VR or V over R?
It's one of those two.
Where did you get the L thing?
L, that's angular momentum.
Oh, okay.
V over R.
So omega is V over R. And therefore, we have 0.6 divided by 1.3, which unfortunately I didn't pick numbers to make this nicer. But that's equal to 6/13 radians per second. In terms of units, this is meters per second. That's meters. The meters cancel out, and you're left with whatever per second. So I now know my initial angular momentum is the angular momentum initially of the ball plus the initial angular momentum of the rod. We have just figured out that this is
Rad per
the
what?
mass of the ball, 1.5.
Dr. Fox?
Yes.
It's a 6/13 rad per what? Per second.
Radians per second.
Thanks.
So 1.5 times 1.3 squared plus, so not 1.3. That is I times omega, which is 6/13.
Where'd you get the LIB and LIR?
The total angular momentum before
Oh, ball in rotation thing?
ball and rod.
Oh, okay.
Is the ball, axis of rotation, so R is just straight.
Is there a question over there, or you're answering?
We were just on.
So then through the magic of a calculator, you end up with some answer that just make life better.
1.17. That may or may not be right. What are the units? The units are obviously obvious.
No, 1.17 can't be right.
That's okay. I can just redo it all.
Oh, wait. That just something careless there.
It's okay, I can just redo it all.
Oh, that might be right, sorry.
1.17.
Yeah, okay. And
How do
you know
we
what the
figure
next
out,
question is gonna be.
how did we figure out M and H? Well, I
M
know
is
how
the
we
mass of the
figure-
ball,
Oh, right.
and H is how far we shifted the axis.
So 1.3 again?
Yes.
You just told me that, dude.
Okay.
Like, he was gonna say
Units?
they weren't gonna get it. The units are obvious.
Yeah.
And where did we get the plus 0?
That's because the rod is initially at rest, so
Just so you can-
Oh.
its angular momentum is 0.
I have a question.
Okay.
Are the, I really just don't know these units, like,
What are the units of 1.5?
Meters. kg.
kg.
Kilograms.
Uh.
The units of 1.3?
I wrote that wrong. Meters.
The units of 6/13?
Rings per over seconds. kg times.
kgm. That's just newtons.
Is that
Or
just-
Newton meters.
Is that is that newtons times radians?
No,
Isn't it Newton meters?
no, it's not a Newton meter.
Is it just a Newton?
Oh, kgm squared over s?
Oh, that's what I got.
Newton is a kilogram meter per second squared. We got the square in a different spot.
I didn't even see the square.
Wait, why are we?
If you want to throw radians in there also,
Because
it's
radians is
not.
Why would we do that?
I don't know why. Some people, for the fun of it,
Some people, huh?
unit fun.
Wait,
Uh-huh.
what is this?
So we have the total angular momentum before this collision.
Yes, we have that. That is true.
Okay, that did a dramatic pause there for questions and apparently comments. What is the total angular momentum after the collision?
Wait, what's the total what? After?
What is the total angular momentum after the collision? Going to word it out. In unison would be really cool right now.
Total momentum?
Total angular momentum after the collision.
Didn't you just write it down? Wait.
Total angular momentum after the collision is 1.17 kilogram times meter second over, kilogram times meter squared over seconds.
Yes, it's the same.
Cause
That's-
motion is conserved.
Yes. That's that whole principle of conservation momentum. The total beforehand is the total afterwards.
Is that not L?
The question I was asking is, what is the total? That's the total right there. That's the total beforehand.
Angular momentum?
Yes,
That's L.
yes.
Oh,
The 2/5?
You've forgotten already.
yes, I have.
On your show?
I forgot what I ate for breakfast this morning, or if I did.
Yours is 2/5 squared.
Now, we could have found the angular momentum a slightly different way.
I don't have that on
Let's see.
That's not, why are we having a 2? That's supposed to say partially.
Angular momentum also is R cross P. R is a vector going from where it begins to where it ends. So R would be a vector actually going in the opposite direction. The moment arm. If I set up an I hat, J hat, K hat, my radial unit vector would be 1.3 meters negative J hat, cross my momentum, which is whatever 1.5 times 0.6 is, that's 0.9 kilogram meter per second I hat.
Wait, where are we getting the 0.9 from again?
The momentum.
Ah.
And so first off, in terms of magnitude, we get 1.3 times 0.9. That's the calculator part, or however you want to do it. And I suspect it comes out somewhere around 1.17. Now we have to get direction, negative J hat cross I hat. I heard negative.
Yeah. Oh my god. Oh, you mean like this thing?
Right. Yeah, there we go.
Hold on, where did we get the
Is it-
negative J hat cross I hat?
Because the angular momentum could also be solved by R cross P. If you think about it, torque is R cross F, sort of a parallel there.
What's negative?
Got I hat going that way, negative J hat down, so I start out with my hand in the direction of the first vector, which is down. I want my fingers to curl towards the second vector the shortest way possible. My thumb points out in the k hat direction. So that's k hat. So I end up with 1.17 k hat. And now the units, I have meters times kilograms times meters over seconds, which is a kilogram meter squared per second. The only thing over here that I could get gigged on is the fact that I didn't give a direction. Well, I hadn't defined the coordinate system at that point, so, but now I have. Yeah. Because if this is my axis and the ball is traveling like that, it points out. Questions to hear?
Can you explain from the blue that's anytime beyond negative j hat cross I hat equals k hat? Like whatever's below that?
Whatever's
The blue that your hand is near.
there, that.
Yes.
So R is the moment arm
Yes.
from the axis of rotation to where the momentum is.
Okay.
It's where the object is. The object's down here, so R is the vector going that way.
Okay.
P is just the linear momentum of the object.
Yeah.
So I did mass times velocity to get 0.9
Okay. Let me write that down.
in the I hat direction.
Okay. So P.
So this is just another
Equals-
way to find the initial angular momentum.
Yes.
So we just found that of the ball or the putty, right?
Correct.
Would it be the same for the rod?
The rod is trickier to use R cross P on because it doesn't really travel in a straight line. If you have something traveling in a straight line, R cross P works great. If you have something that's rotating, I omega is the easier path to take.
Can you explain R again? The
Moment arm,
yeah.
sometimes referred to as lever arm. It's just a vector, in the case of torque, that's where we dealt with it the first time.
Okay.
R is a vector from the axis of rotation to where the force is applied.
Okay.
All right, so we have ball being shot, hitting putty. We have the total angular momentum beforehand, two different ways. Now afterwards. Because this thing is rotating after the collision, I omega is going to be a simpler way of doing it. I know that my initial angular momentum equals my final angular momentum. So I have 1.17
Oh, I'm done that.
is technically k hat is equal to afterwards, which is I final omega final.
Is the moment arm the same as the height?
The magnitude of the moment arm is the height, and
Okay.
it's how far we shifted the axis in this case. That's not a universal.
Okay. Why did you underline it? Unless that's divided by.
The underline the 1.3 and the 0.9.
Yeah.
I suspect, I don't remember exactly, but I suspect it's because I mentioned those two numbers. I think
So
somebody
it's
asked me where they came
insignificant.
from, and I underlined it as I
So
was
it's
talking about it.
insignificant.
No,
It is significant? Or
it's not significant.
Okay.
Okay.
That's what we're trying to find, so we need to figure out what that is. So, how do you find the moment of inertia of this rod-putty combination? if you recall. Ultimately, if we went back to the beginning, the moment of inertia is the sum into I r sub I squared, I equals 1 to technically infinity. It's just a sum. It's a sum of all the tiny little masses, infinite sum of infinitesimally small masses times the distance squared. What this is, hopefully, I would like you to connect with is that this means, since it's just a sum, I could do the putty and the rod separately in terms of finding the moment of inertia. So I final would be I final of the ball plus I final of the rod. I final of the ball is whatever we had before. We didn't actually calculate it. So this is going to be mass of ball times distance, we move the axis squared for the ball, plus that for the rod. Whatever the, so how do you find the moment of inertia of the rod? Are you stopping there?
No. No, I'm not.
What is this formula that Moron just told us?
Isn't that if the axis of rotation for the rod would be straight in the middle?
Yes.
So then we would have to do the parallel axis there?
Yes, we would. That's the formula for about the cinder. We are shifting the axis from here to here. So from 1 meter from the top to 0.4 from the top. So I guess it'd be 0.6. Plus mass, oh, that's rod. Mass of rod times how far we can shift the rod axis. So at this point, plug it in numbers. This was 1.5 times 1.3 squared plus 1/12 times.
Where'd we get 1/12?
That's from the inertia formula for a
Oh.
rod.
Rotating about its central axis. Times 2 squared plus 3.5 times 0.6 squared. And then with the magic of a calculator, or whatever device you have to be using. So I'm just going to reveal the magic answer.
My calculator's dead.
I got 4.96.
For the whole thing?
4.962.
That seems awfully low.
I got 27.77.
27 point
77, then 6 inches per infinity. So,
7 repeating.
yeah, actually.
Is that suspicious?
Okay, I did. No, I didn't. I put everything in.
Remember to square?
Let me try again.
Well, because that's about, crudely, that's about 1. That's 2 point something. That's about 4. Actually, the 4.962 is making more
Well,
sense.
no, what you got is correct. I forgot the decimal place. I thought that was 15.
Yeah. Sorry, Aaron,
Oh, okay.
that was, sorry, and I heard somebody start mumble units.
Kilograms times meters squared per second.
No.
Oh my god, what?
This is moment of inertia, this isn't angular momentum.
Oh, well, inertia. Oh my god, why did I think that? What's the units of kilograms times meters squared per second.
That's what you just said.
Why is it different from the other one?
Because the other one was angular momentum, this is
Because
moment of inertia.
Oh, the answer is, wow. The answer is, I know what it is.
Do you?
Yeah, I'm almost there.
Is it mr squared?
It would be the units of mr squared.
Wait, inertia is mass, right? Oh,
This is moment of
Inertia?
wait, moment of inertia, god dang.
Alright, units of mass,
Kilogram.
units of r
Here.
squared, it's just kilogram meter squared.
What is on there?
Alright, so we know what I is afterwards, so 1.17 is equal to 4.962 omega, final. So my final angular speed, just that fraction right there, 1/3. That's not right.
1.17 divided by 4.962.
Yes.
0.2358.
Units?
Radians over seconds. Yes, I got one. Okay.
Alright, this conservation of angular momentum. Remember that